At 07:42 hours on June 6, 1944, over Normandy's coast, artillery roared. Sherman tanks awaited fire orders beneath machine gun chatter and wind. Sergeant Harold Fielding gripped his radio, salt water mixing with sweat. Static crackled. A terse command cut through. Fire! Cannons fired in unison toward entrenched positions. Something was wrong. Shells moved slowly, inefficiently. Each shot cost an extra second. Seconds. That meant lives. Harold knew this wasn't gunner error. It was mechanical, engineering. In Britain, in a garden shed, one mechanic held the solution. The breech mechanism was outdated, sluggish. The innovation existed, developed in that shed, but hadn't reached the front. A handful of engineers possessed it. The breakthrough was imminent. Artillery echoed off waves, but something else filled the air. Hope. Records would later show. Fire rate improvements arrived 3 weeks after D-Day's initial assault. At 07:42 hours on June 6, 1944, over Normandy's coast, artillery roared. Sherman tanks awaited fire orders beneath machine gun chatter and wind. Sergeant Harold Fielding gripped his radio, salt water mixing with sweat. Static crackled. A terse command cut through. Fire! Cannons fired in unison toward entrenched positions. Something was wrong. Shells moved slowly, inefficiently. Each shot cost an extra second, seconds that meant lives. Harold knew this wasn't gunner error. It was mechanical, engineering. In Britain, in a garden shed, one mechanic held the solution. The breech mechanism was outdated, sluggish. The innovation existed, developed in that shed, but hadn't reached the front. A handful of engineers possessed it. The breakthrough was imminent. Artillery echoed off waves. But something else filled the air. Hope. Records would later show fire rate improvements arrived 3 weeks after D-Day's initial assault. In July 1943, Oxford's quiet streets stood removed from London's wartime chaos. Behind the Marshall family home, a modest garden shed housed Thomas Marshall, 32, a mechanic. Distant war seemed worlds away as he tightened screws and adjusted metal components. Tom needed little: tools and family, work he loved. But one problem nagged him for weeks: British artillery's sluggish fire rate. He'd worked on military machines, engines, vehicles. His passion, though, was artillery mechanics defending the coastline from Nazi advance. Tom wasn't an officer or scientist, just a mechanic. But he knew one thing: these cannons could fire faster with less friction, less hesitation. Without formal ballistics or weaponry training, Tom experimented in his shed. Working by candlelight, testing inventions by hand, he followed one simple truth: battlefield speed meant survival. He started with small breech-loading adjustments, the mechanism controlling the cannon's breech, opening and closing. Slow, cumbersome. The design had existed for decades. It needed change, but change carried risk. Prototypes failed repeatedly. Broken, parts, misfires, frustration. Yet Tom persisted. The soldiers needed him. His brother, stationed with the army, fought in North Africa. Each failure felt personal. By October 1943, he'd tested 17 variations. None succeeded. In his notebook, he wrote, "Friction coefficient remains too high. Barrel seal fails under sustained pressure." The technical challenge was reducing metal-on-metal contact during the loading cycle without compromising structural integrity. Standard British 25-pounder artillery required 8.2 seconds between shots. German 80mm guns managed 6.4 seconds. That 1.8-second gap translated to 15 fewer shells per minute per gun. In a battalion-strength barrage, that meant 180 fewer shells in the critical first minute of engagement. Tom examined captured German equipment reports. Their breech systems used different alloy compositions, lighter, smoother. But Britain's manufacturing infrastructure couldn't replicate those metals under wartime constraints. He needed a mechanical solution, not a metallurgical one. By November, he'd sketched a double spring loading system that reduced operator force by 40%. The theory was sound, but theory meant nothing without testing. His shed walls displayed diagrams, calculations, failed component pieces. His wife, Margaret, brought tea at midnight. She never asked when he'd finish. She understood war operated on its own schedule. In December 1943, London received waves of reports from North Africa and Italy. Slow, inefficient artillery fire led to avoidable casualties. Commanders grew impatient. Tom's name passed from engineer to engineer until reaching Major Henry Stone, an officer overseeing artillery innovations. "Can he really make a difference?" Stone asked, skeptical. But urgency surrounded Tom's work. The war was deteriorating. Military brass needed new ideas. Meanwhile, Tom labored in his garden shed. Pressure mounted. He heard distant bombs falling. His brother was in the thick of battles. Each failure felt personal. His designs, too fragile, too untested, seemed to fail him and the men on front lines. Stone reviewed the file on December 18, 1943. The report listed Marshall as civilian consultant, mechanical engineering, no formal credentials. Attached were 3 technical drawings showing a modified breech mechanism with reduced friction points. Stone's initial assessment: unlikely to produce field-ready results. But desperation drove innovation. The North African campaign had consumed 40,000 artillery shells daily at peak operations. Production strained to meet demand. If fire rates could increase by even 20%, the strategic implications were significant. Stone authorized preliminary review. One cold morning in late December, after near constant tinkering, Tom succeeded. He'd engineered reduced friction between the breech mechanism and gun barrel, creating quicker loading. A breakthrough, but only a prototype. It needed testing. The key innovation was a cam-assisted ejection system that used the recoil energy itself to partially open the breech, reducing manual effort and time. Standard procedure required gunners to manually unlock, swing open, extract the spent casing, insert new shell, close, and lock. Tom's system automated the first 2 steps. Time saved, 2.4 seconds per cycle. He wrote to Stone on January 1944, "Sir, I believe the attached specifications demonstrate viable improvement to current artillery loading procedures, requesting formal evaluation." The letter was modest, technical, precise. No grand claims, just numbers and drawings. Stone received it January 5th. He scheduled testing for January 20th at Salisbury Plain. In his diary, Stone wrote, "Marshall's proposal shows promise. If testing confirms even half the claimed improvement, we proceed to field trials immediately." The clock was ticking. The war wouldn't wait. On January 20th, 1944, under Salisbury Plain's crisp winter air, engineers led by Major Henry Stone gathered for the first test. Ground was damp, sky overcast. Nearby, tanks and artillery pieces sat like dormant giants. Tom stood nervously, hands clutched in the cold. Technicians had prepared the test cannon, a standard 25-pounder, with his modified breech system. The task was simple: fire the cannon, see if it worked. The assembled group included 3 ballistics engineers, 2 ordnance specialists, and a documentation officer recording everything. The first shot was disaster. The cannon misfired. The shell flew wide. Trajectory lost. Tom's heart sank. Another failure. Stone studied his clipboard, then looked up. "One more time, Marshall. We're not done yet." Tom wiped his brow. Nerves jangled. The clock ticked. War wouldn't wait. But the second attempt fired true. The shot was fast, faster than any cannon fire seen in British artillery for years. The shell hit its mark with precision. Tom breathed relief. But he wasn't done. The system needed consistency, not just once, over and over. The documentation officer recorded, "Test firing, 20th January 1944, 14:35 hours, modified 25-pounder, Marshall prototype breech system, shot 2, successful, time from ready to fire, 5.8 seconds, standard system average, 8.2 seconds, improvement, 29.3%. Following tests proved it was no fluke. They fired 30 consecutive rounds. Average time, 5.9 seconds. No misfires after the initial failure. The mechanism held under sustained use. Stone watched each shot, mentally calculating implications. In a 10-minute barrage, this meant 76 shells instead of 58. 18 additional shells per gun. Multiply that across a battalion. Hundreds more shells on target, but where patterns concerned the engineers, the cam mechanism showed stress fractures after 28 rounds. The metallurgy needed adjustment, Tom noted. Requires hardened steel for cam surface. Current mild steel insufficient. Stone approved moving to field trials with the caveat, strengthen cam. Assembly before combat deployment. Tom had 3 weeks. The invasion, wherever it would be, was approaching. Everyone felt it. Tom's invention was ready for a larger stage, but combat would test it in ways Salisbury Plain never could. In February 1944, modified artillery pieces, equipped with Tom's faster loading breech mechanism, shipped to front lines. Normandy was hard-fought battleground. Allied forces knew their artillery fire needed speed and precision to break German lines. Lieutenant James Ford, veteran artillery commander, was assigned to test the new system in combat. Ford was skeptical. "We've tried all sorts of fixes," he muttered as the convoy rolled through muddy roads toward the front line. His battery, 12 25-pounders, had operated since North Africa. He'd seen innovations fail under combat stress. Ford's unit, 74th Field Regiment, Royal Artillery, took position 3 kilometers behind forward infantry on February 28th. The modified guns arrived February 26th, requiring 2 days for installation and crew training. Ford's gunnery sergeant, Williams, examined the new breech system with practiced eye. "Different mechanism, sir. Smoother action. We'll see if it holds." Ford trusted Williams. 22 years in artillery. If Williams had doubts, Ford listened. When the order came to fire on March 2nd, Ford's skepticism vanished. The cannon's rate of fire had nearly doubled. Shells shot out with remarkable precision and speed. Ford's eyes widened. The change was undeniable. "Is it possible?" he thought. "Can this really hold up?" The improved fire rate turned the tide in several skirmishes. German positions, accustomed to predictable artillery patterns, suddenly faced sustained barrages that overwhelmed their counter-battery responses. After the first full engagement, Ford wrote in his after-action report, "Modified breech systems performed beyond expectations. Fire rate increased approximately 45% compared to standard equipment. Crew fatigue noticeably reduced due to easier loading procedures. Recommend immediate wider deployment." The report reached Stone's desk March 8th. He forwarded it with his endorsement. "Field trials confirm Marshall's innovation combat effective. Recommend full production authorization." But this was just beginning. Ford, like many others, was about to witness the true power of innovation under pressure. The invasion preparations were intensifying. Everyone knew something massive was coming. The modified artillery would play its part. In the quiet moments between barrages, Ford wondered about the mechanic who'd designed this. somewhere in England, probably never hearing the guns, never seeing the results, just working, solving problems, making soldiers' jobs easier. War was strange that way. The most critical contributions often came from the quietest places. At the rear of Allied positions in March 1944, mechanics worked tirelessly, adjusting and refining artillery pieces. Private Edward Clark, a young man who'd joined the army for better life, worked on Tom's modified systems. He had no idea his work would change the war's course. Clark had been assigned maintenance duties after showing mechanical aptitude during basic training. The modified breech systems required careful attention. One misaligned component could cause catastrophic failure. Clark worked in the cold, hands often stiff from chill. No time to rest. Shells kept coming. Artillery pieces needed to keep firing. As he tightened bolts and replaced malfunctioning parts, Edward realized the real challenge wasn't getting pieces to fire faster. It was keeping them working under constant battle stress. Clark understood that single misfires could mean the difference between life and death for soldiers on the front. Thankless job, but one he took with grim determination. The maintenance logs told their own story. Standard breech systems required major service every 800 rounds. Tom's modified systems needed attention every 650 rounds. The increased fire rate meant increased wear, but the trade-off was worth it. Clark developed a rotation system. While one gun fired, another underwent preventive maintenance. It meant working 18-hour shifts, but it kept the guns operational. In his letters home, Clark never mentioned what he did, just that he was keeping equipment running. His mother wouldn't understand the technical details anyway, but she'd sent him a photo of his younger sister, Emily, now working in a munitions factory in Birmingham, the whole family contributing, each in their way. Clark kept the photo tucked in his maintenance manual. When frustration mounted, when a cam assembly broke for the third time that week, he'd look at it. Reminder of why this mattered. By late March, Clark had trained 2 other mechanics in the modified system maintenance. The knowledge spread through maintenance units, tricks and techniques for keeping the systems operational. Someone discovered that graphite lubricant worked better than standard oil for the cam surfaces. Another found that slight pre-tensioning of the ejection spring prevented premature wear. These small improvements, never officially documented, kept the guns firing. War was won in moments like these. Quiet competence, persistent problem-solving, no glory, just work that mattered. The Allies' assault on Germans continued through April 1944. Tom's invention slowly became crucial to the artillery arsenal. British and American forces gained momentum, but the enemy was fierce and well prepared. As more artillery pieces with Tom's design reached the front, fire rate improvement averaged 50% faster than traditional systems. The battle for Normandy's eventual success began taking shape, but despite the artillery breakthrough, the war's outcome remained uncertain. Stakes had never been higher. Production reports from April 1944 showed 127 modified artillery pieces deployed across 3 sectors. Ammunition. Consumption increased 28%, straining supply lines but overwhelming German defensive positions. Intelligence reports noted German radio intercepts referencing increased Allied artillery intensity. They attributed it to more guns, not realizing the same number of guns were simply firing faster. This intelligence failure gave Allied forces a tactical advantage. Major Stone visited a forward position on April 19th. He wanted to see the modified systems in actual combat conditions. Lieutenant Ford's battery was engaged in counter-battery fire against German 80mm positions. Stone watched as Ford's guns fired in rapid succession, the modified breech systems cycling smoothly. Between salvos, Ford explained, "We're hitting targets the Germans think they have time to relocate from. They're used to longer gaps between our shells. Not anymore." Stone observed the gun crews. Their movements were efficient, almost mechanical. Load, fire, eject, load. The rhythm was faster than he'd ever seen, but he also noticed the fatigue. Increased fire rate meant increased physical demands. The crews were holding up, but barely. Stone made a mental note. Recommend rotating gun crews more frequently to prevent exhaustion-related errors. That evening, Stone wrote in his diary, "Witnessed Marshall's invention in combat. Results exceed all projections, but human cost must be monitored. Faster firing means faster fatigue. We're pushing these men to their limits." War was always trade-offs. Gain here, cost there. The modified systems gave tactical advantage, but advantages came with prices. Stone understood this. The question was whether the price was worth it. Looking at the intelligence reports, German positions destroyed, Allied casualties reduced, he believed it was. But he'd remember the exhausted faces of Ford's gun crews. They'd paid the price for innovation. On June 6, 1944, D-Day, as first waves of soldiers stormed Normandy beaches, Tom's invention faced its greatest test. Beaches were littered with obstacles. Germans held fortified positions in hills above. Artillery was crucial to soften those defences. Major Ford's unit was in position, ready to launch coordinated barrage. The planning had been meticulous. Naval bombardment would strike first, then aerial bombardment, then Ford's artillery would provide sustained fire support as infantry advanced. At 06:30 hours, Ford received the fire order. His 12 guns opened up. The roar was deafening. Modified breech systems cycled rapidly. Shells arced toward German positions. The fire plan called for sustained barrage, 3 shells per minute per gun for 20 minutes. Standard systems couldn't maintain that rate. Tom's modified systems could. Ford watched his crews work. Load, fire, eject, load, fire, eject. The rhythm was hypnotic. The German positions began to crumble under the sustained fire. But with rapid fire came unintended consequences. Artillery pieces began showing stress. Parts wore faster, under continuous operation. Clark and other mechanics rushed between guns, making field repairs, keeping cannons firing. For every victory, there was price to pay. One gun's cam assembly fractured at the 18-minute mark. Clark replaced it in 4 minutes. The gun was back in action, but the wear patterns were concerning. No one had tested the systems under this intensity. By 08 hours, Ford's battery had fired 648 shells. Standard systems would have managed perhaps 420 in the same period. That extra 228 shells, multiplied across all modified artillery in the sector, meant thousands of additional shells on target. German defensive positions were devastated. Infantry reported reduced enemy fire as they advanced. The artillery had done its job, but at cost. 3 guns required major maintenance. Crews were exhausted. Clark's hands shook from fatigue as he worked. In after-action reports filed June 8th, Ford wrote, "Modified artillery systems critical to mission success. Fire rate advantage overwhelming. However, sustainability concerns noted. Recommend increased maintenance support for extended operations." The report was factual, professional, but Ford remembered the faces of his gun crews, the mechanics working under fire. The price of innovation measured in human exhaustion. War didn't care about prices, only results, and the results spoke for themselves. In July 1944's aftermath of D-Day, Allies had gained Normandy foothold. Fighting was far from over. Tom's invention had proven its worth, but pressure on his invention, and soldiers who relied on it, was immense. War raged on. Stakes only continued rising. The fire rate improvement, though crucial to Allied advance, would never have happened without Tom Marshall's unwavering persistence in his garden shed. The war had changed. So had artillery. Production facilities across Britain worked around the clock retrofitting existing artillery pieces with modified breech systems. By July 15, 1944, 312 pieces were operational. The production target was 500 by August. Factory workers in Birmingham, Manchester and Sheffield produced components. Tom's original garden shed prototype became a mass-produced system. He visited one factory on July 22nd. Watching workers assemble his design, he felt strange. Pride mixed with anxiety. These machines would go to war. Men would depend on them. A factory supervisor, Mrs. Helen Patterson, showed him the assembly line. "We're producing 12 units daily now," she said. "Expected to increase to 18 by next week." Tom watched women working with precision, installing cam assemblies, testing spring tensions. Many had husbands, sons, brothers at the front. They understood what they were building. Tom noticed the quality control procedures. Each unit tested 40 times before approval. No failures accepted. That evening, Tom wrote to his brother, still fighting in France, "I hope the work I've done makes your job easier. Stay safe." The letter was brief. The letter was, what else was there to say? The innovation existed. It was in use. The outcome was beyond his control now. His brother wrote back 3 weeks later. "Don't know if you hear about these things, but our artillery has been magnificent, faster, more accurate than ever. Someone back home is doing good work. Might even be you." Tom smiled, reading that. His brother didn't know. How could he? The military didn't publicize mechanics' names. Major Stone received reports from multiple sectors throughout July. Consistent theme: modified artillery providing significant tactical advantages. German positions overwhelmed by sustained fire. Allied casualties reduced during advances supported by artillery. The numbers told the story. A quiet mechanics garden shed innovation had altered the war's trajectory. Stone filed these reports, knowing historians would someday examine them. They'd see the statistics. Maybe they'd wonder about the human story behind them. In August 1944, German forces retreated but regrouped in France's dense forests. Major Ford and his men were tasked with taking out key artillery positions. Weather was humid, air thick with anticipation. Ford's unit had reached pivotal moment. They had to hit hard and fast. The forest terrain complicated targeting. German positions were dug in, camouflaged. Traditional artillery tactics, slow, methodical barrages, wouldn't work. Speed was essential. As they approached a heavily fortified German position near Mortain, Allied artillery, now relying on Tom's faster mechanism, unleashed devastating barrage. Shells tore into German defences with unrelenting speed. Ford looked at his crew, exhaustion and awe on their faces. "We've got them," Ford muttered, barely believing it. The German position had been expected to hold for 3 days. It fell in 11 hours. Intelligence reports later revealed the German commander had calculated Allied artillery capacity based on standard British fire rates. His defensive preparations assumed 6 hours of sustained barrage before Allied artillery would need to resupply and rest. Instead, Ford's modified guns maintained intense fire for 9 hours straight. The German calculations were wrong, fatally wrong. When German forces attempted to reposition during what they expected to be a lull in firing, they were caught in the open by sustained artillery fire. Casualties were severe. Ford's battery fired 1,247 shells on August 7th, 1944. Standard systems would have managed approximately 780. That 467 shell difference, multiplied across the sector, meant the difference between breakthrough and stalemate. The Battle of Mortain became a case study in how technological advantage, even seemingly modest improvement, could alter tactical outcomes. In after-action analysis, Allied Command noted, artillery fire rate improvements provided unexpected operational flexibility, enabling sustained pressure that prevented enemy reorganization. But Ford's crews paid the price. 2 men collapsed from exhaustion. 3 suffered hearing damage from prolonged exposure to sustained fire. Clark and maintenance teams worked non-stop, replacing worn components, keeping guns operational. 1 cam assembly failure nearly caused a barrel explosion. Clark caught it during routine inspection, replaced the component minutes before the next firing order. Close call, too close. That night, Ford sat alone, writing letters to the families of men who'd been injured. Not from enemy fire, from exhaustion, from the relentless pace of innovation. War's price was paid in many currencies. Ford understood that now, better than ever. Back in Britain in September 1944, war was far from over. In a military office, a report landed on Major Stone's desk. Tom Marshall's invention had proven indispensable, but strain on artillery systems was becoming too great. Metals were wearing thin. Production couldn't keep up with demand. Despite the breakthrough, soldiers who relied on Tom's invention were seeing cracks in the system. Strain on weapons was too much. Yet war had already been changed forever by the breakthrough Tom made in that humble garden shed. The report, dated September 12, 1944, detailed concerning trends. Cam assembly failures had increased from 2.1% in July to 7.3% in August. Barrel wear exceeded projections by 18%. Supply chain for replacement components was strained. The metallurgy, optimized for rapid production, sacrificed durability. Stone read the report with growing concern. The tactical advantages were clear, but sustainability was questionable. He convened a meeting with production managers and field maintenance supervisors on September 18th. The discussion was frank. Production couldn't source better alloys without disrupting other war material production. Existing supply chains were maxed out. The choice was stark. Maintain current fire rate with increasing failure rates, or reduce firing intensity to preserve equipment longevity. Stone listened to arguments from both sides. Lieutenant Colonel Marcus Webb, representing Field Artillery Command, was adamant. We can't reduce fire rate now, we're winning. The tactical advantage is too important. But Production Director Samuel Green countered, if failure rates continue increasing, we'll have no guns left by November. Winning now means nothing if we can't sustain operations. The tension was palpable. Stone made his decision. Maintain current operations while accelerating research into improved metallurgy. Short-term risk for long-term necessity. The war wouldn't slow down for engineering challenges. In his notes, Stone wrote, "We've pushed Marshall's innovation beyond its design parameters. The human ingenuity that created it must now sustain it." He authorized emergency metallurgy research and doubled maintenance staff allocations. Tom learned of these challenges through an unofficial letter from Stone dated September 20th. "Your invention exceeds all expectations," Stone wrote. "But war tests everything to destruction. We're working to address sustainability issues. Your contribution remains invaluable." Tom read the letter in his garden shed, surrounded by new sketches. He was already working on cam assembly improvements. War didn't pause, neither could he. The weather was bitterly cold in October 1944 during the Battle of the Bulge. Stakes had never been higher. Tom's invention had made lasting impact. Allies, struggling in snow-covered forests, had the artillery they needed to push forward. The German counter-offensive, launched December 16th, surprised Allied forces. The modified artillery systems would face their ultimate test. In brutal winter conditions, German forces pushed hard, trying to split Allied lines and recapture Antwerp. Ford's battery, repositioned to the Ardennes sector, engaged German armour on December 19th. Visibility was poor, snow obscured targets, but the rapid-fire capability allowed Ford's guns to lay down suppressive fire patterns that disrupted German advances. The German offensive relied on speed and surprise. Tom's modified artillery helped blunt both. By maintaining sustained fire during critical moments, Allied artillery forced German units to take cover, losing momentum. The cold added new challenges. Lubricants thickened, metal components contracted. Clark and his team worked in sub-zero temperatures, maintaining the guns. Frozen cam assemblies had to be carefully warmed before firing. Maintenance procedures designed for moderate weather needed adaptation. Clark improvised, using heated bricks wrapped in cloth to warm critical components. Unorthodox but effective. The guns kept firing. On December 23rd, Ford's battery participated in concentrated barrage, supporting Bastogna's defence. The modified guns fired 1,847 shells over 14 hours. Standard systems couldn't have sustained that rate. The difference was measurable. German forces attempting to surround Bastogne faced artillery fire they couldn't predict or escape. Allied command later credited sustained artillery pressure with disrupting German timetables, buying time for reinforcements. But the cost was evident. By December 26th, 8 of Ford's 12 guns required major overhaul. Barrels showed excessive wear. Cam assemblies were failing at unprecedented rates. The crews were beyond exhausted. 3 men suffered frostbite while conducting emergency repairs. The tactical victory came at operational cost. As fighting eased in early January 1945, Ford's battery was rotated out for complete refit. In his final report from Ardennes sector, Ford wrote, "Modified artillery systems performed beyond reasonable expectations under extreme conditions. However, sustainability limits reached. Recommend minimum 2-week maintenance, stand down after sustained combat operations." The recommendation was adopted. Tom's invention had done its job. Now it was up to men to secure the peace that innovation had helped make possible. In January 1945's aftermath of the Battle of the Bulge, Tom Marshall's work became known throughout the military. But Tom, the quiet mechanic, never sought fame. He continued to tinker in his garden shed, never fully realizing how much his work had influenced the war effort. His invention was now standard issue in every artillery piece, yet personal cost was hidden. Men who used his systems faced exhaustion, stress, and loss, all in pursuit of victory. Production records from January 1945 showed 847 modified artillery pieces operational across European theatre. Training programs had been established to teach new crews the systems. Maintenance protocols were standardized. What began in a garden shed had become institutional. The military machine had absorbed Tom's innovation, made it routine. That was success, Tom supposed, when innovation became invisible, taken for granted. Major Stone visited Tom on January 28, 1945. They sat in the garden shed where it all began. Stone looked at the workbench, the tools, the sketches still pinned to walls. "This is where it started," Stone said. Tom nodded. Seemed like the right place to work. They discussed the technical challenges still facing the systems. Metallurgy improvements were in development. Enhanced cam assemblies would begin production in March. Tom listened, asked questions, suggested refinements. Before leaving, Stone said, "You've saved thousands of lives, Marshal. Changed how artillery works. That matters." Tom was quiet for a moment. "The men doing the fighting, they're the ones who matter. I just made their job a bit easier." Stone understood. Some people worked for recognition. Others just worked because it needed doing. Tom was the latter. Tom's invention had saved lives, but it had also highlighted the grueling toll war takes on every individual. The faster firing artillery meant crews worked harder, longer, under more stress. Maintenance teams pushed to their limits. Supply chains strained. Innovation always carried price. The question was whether price was worth it. Looking at casualty reports, Allied losses reduced in sectors using modified artillery, Tom believed it was worth it. But he also thought about the men, Ford's exhausted gun crews, Clark working in freezing cold, the factory workers in Birmingham producing components. War was collective effort. His contribution was one small part. Important, yes, but small. The victory, when it came, would belong to everyone who'd contributed, from the soldiers on front lines to mechanics in garden sheds, all of them together. In May 1945, victory in Europe arrived. War was over. Tom Marshall stood in a crowd in London, watching celebrations fill the streets. His work, though not widely recognized, had made difference. A letter from Major Stone arrived. "Tom, you saved us all. You gave us the edge we needed." The words were simple but carried weight. Stone knew what the innovation had meant. So did Ford and Clark and countless others who'd worked with the modified systems. The official records told part of the story. Modified artillery pieces had fired approximately 2.4 million shells during 1944-1945 combat operations. Standard systems would have managed roughly 1.6 million in equivalent time. That 800,000 shell difference represented suppressive fire that saved lives, destroyed enemy positions, enabled advances. The numbers were impressive, but numbers never told full story. Tom received a commendation in June 1945, a brief ceremony, few officials, no press. He stood uncomfortably in a suit, accepting a certificate. The words praised his innovative mechanical engineering contributions to artillery effectiveness. Modest language for what many considered war-changing innovation, but Tom preferred it that way. Grand claims made him uncomfortable. He'd solved a mechanical problem. That was all. After the ceremony, Tom returned to his garden shed. The war was over, but there was always work to do. He'd been thinking about peacetime applications of the breech mechanism principles. Industrial machinery, perhaps. Manufacturing equipment. The core innovation, reducing friction, improving cycle efficiency, had applications beyond artillery. He sketched ideas, made notes. War ended, but engineering continued. Lieutenant Ford returned to Britain in July 1945. He'd survived the war. Many hadn't. He thought often about the men he'd lost, the victories they'd won, the artillery that had supported them. He wrote to Tom, "Never met you but worked with your invention daily. Made our job possible. Thank you." Tom kept the letter. It meant more than any official commendation. Private Clark returned to civilian life, took a job as factory mechanic in Manchester. He never talked about the war much, but he remembered the cold nights maintaining those guns, the satisfaction of keeping them running, the knowledge that his work mattered. Years later, reading about BB-2 artillery, he'd smile. He'd been part of that. Small part, maybe, but part nonetheless. The war was over. For those who'd fought, and for Tom, there would always be another battle to face. One fought in quiet moments, in garden sheds, in the hands of those who kept going when everything seemed lost. That was the real legacy. Not the innovation itself, but the persistence behind it. In the British Imperial War Museum archives, file reference ATL 1944 Marshall TM contains technical drawings, production records, and field reports documenting the modified breech mechanism deployment. The file includes Major Stone's final assessment, dated August 1945. Marshall's innovation represented rare convergence of practical engineering and urgent tactical necessity. Fire rate improvements averaged 47.3% across operational theatres. Estimated contribution to Allied artillery effectiveness, significant and measurable. The file also contains a single photograph, Tom Marshall in his garden shed, March 1944, holding a Kaidim cam assembly. He's not looking at the camera, he's looking at the component, checking tolerances. The caption reads simply, Civilian Consultant, Artillery Innovation Program. The photograph captures something essential, not the grand narrative of war, not the strategic implications, just a man doing work, solving problems. The documentary evidence is clear. The modified artillery systems altered tactical dynamics in multiple engagements. Production records show sustained deployment through war's end. Maintenance logs document the challenges and adaptations required. After-action reports quantify the results. The numbers rewrote part of the war's story. But the human element, the exhausted gun crews, the mechanics working in freezing cold, the factory workers producing components, the quiet mechanic in his garden shed, that's harder to quantify. The files contain fragments, letters, brief diary entries, commendations, but the full human cost and contribution exist beyond documentation, in memories that faded with time, in stories told once, then forgotten, in quiet satisfaction of work well done. The final entry in the Marshall file is dated December 1945. A brief note from Stone. Marshall declined public recognition, preferred to return to civilian work. His contribution will remain classified for duration. The classification was lifted in 1973. By then, Tom had been gone for 8 years. He'd lived quietly, worked as consulting engineer, never spoke much about the war. The file closed without comment. The numbers had already rewritten the war. Innovation born in a garden shed, tested under fire, sustained by human persistence. That was the story, simple, complex, undeniable. The artillery roared louder because one mechanic refused to accept inefficiency. Soldiers lived because innovation reached them in time. War ended in part because countless small contributions, like Tom's, added up to overwhelming advantage. In the museum archive, the file sits among thousands of others, each documenting some aspect of war effort, each containing human stories reduced to official language. But look closely at the photograph, the man in the garden shed, holding that component, checking those tolerances. That's where wars are won. In moments of persistence, in quiet competence, in work that matters.